Hello everyone, welcome to 2.1 Motion, video 2 of 2. So here is the slide that we left off with last time, so we'll move on to projectile motion now. Projectile motion really just comes down to this. If you take a baseball and you throw it in the air and it travels through some kind of parabolic path, that object is now a projectile. Projectile motion means that an object is only under the influence of the force of gravity. So, for example, if you have an object sitting on your table right now, it's not just the force of gravity that's acting on it, but also the normal force. The table is pushing back up on the, let's say, on the cup. If you have a mug of coffee on your table, its weight is pushing down on the table, and the table then pushes back up on the mug. Otherwise, the mug would collapse right through the table. So baseballs, stones, bullets, these are all examples of objects executing projectile motion because while they're moving through the air, the only force acting on them is gravity. Now, something like an airplane or anything with a jet engine would not be considered a projectile because they are not just moving through the air under the influence of gravity, they're moving through the air under the influence of some kind of thrust force. Okay, so this would be some sort of parabolic path. Okay, so that's your projectile motion. Now, projectile doesn't necessarily have to move up first and then come down. You could just as easily launch some kind of an object horizontally off of a cliff, and it would still follow a curved path until it hit the ground. That is also a projectile, since the only force acting on it would be gravity. Now, for our cases, we generally ignore the presence of air resistance. Air resistance does influence a lot of factors when it comes to calculating how the projectile moves or graphing how it moves. Air resistance is pretty easy to understand. If you sit in a stationary car and stick your hand out the window, you won't feel anything if there's no breeze that day. But if the car is moving and you stick your hand out the window, you'll feel all the air pushing against your hand. And the faster the car goes, the harder it gets to keep your hand in the same position because of all the air resistance hitting it. So for our purposes, we mainly ignore air resistance. If we don't, it will be specified. Okay. Now, in an earlier video, we saw that we can take a vector quantity. So remember that a vector is a quantity that has magnitude and direction. Examples would be velocity, displacement, acceleration, force, and there's so many others. You can take a vector and you can resolve it into its horizontal and its vertical components. Now, the main reason that we do this is because the horizontal and vertical motions of an object are independent of one another. And this is especially true in projectile motion. When we actually start doing the calculation problems, which you'll see later in this video, you'll see how important it is to keep the x and y dimensions of the calculations separate. So here in this picture, we have a baseball, and this baseball is being thrown up into the air, not vertically up, but thrown across some kind of a distance. And that's the kind of parabolic path it's going to take. So if we take a snapshot of that baseball's motion at every point in time, or rather at equal intervals of time, it's going to look something like this. So something to pay attention to is that in the beginning and at the end, the spacing between the baseballs is larger, and at the very top, the spacing is much smaller. Think about why that might be. Now on your screen, you're going to see a blue circle and a red circle. The red circle represents the horizontal motion of the baseball, and the blue circle represents the vertical motion, similar to how we had a vector in an earlier video, and we used green arrows to determine and show the shadows in the x and y directions respectively. All right, so here we go. So there would be the next red and blue dots, and the next ones, the next ones. Okay, so we're at the top, and now we're moving back down. Now, looking at those red dots, what you notice immediately is that they're all evenly spaced. But when you look at the blue dots, the vertical motion, the spacing is originally large, and then it gets smaller and smaller and smaller and smaller and smaller. And on its way down, it starts with small spacing and gets bigger and bigger and bigger and bigger. So what can we conclude about the motion in the horizontal direction? Well, we can conclude that the object is moving at a constant velocity in the x direction. Okay? But in the vertical direction, we can clearly see that the ball is slowing down and then speeding up. Well, if an object changes its velocity, we know that there must be an acceleration present. By definition, acceleration is the rate of change of velocity with respect to time. So think about that. What type of acceleration is present in the vertical direction? If you answered acceleration due to gravity, you are correct. Okay, so we have that g acceleration, which is 9.81, sometimes approximated as 10 meters per second squared in the vertical direction. And that is what's causing it to slow down and speed up respectively. But again, in the horizontal direction, we have no acceleration because the speed is constant. This is a very important consequence and property of projectile motion, which you must remember. In the y direction, we have acceleration, which is that due to gravity. In the x direction, we have zero acceleration and constant speed. Okay, in the absence of air, the trajectory of a projectile is parabolic. Okay, so it looks like a quadratic function. Now, if you have air resistance, also known as fluid resistance, the word fluid can represent a gas or a liquid. Okay, not a solid, just a gas or a liquid. So air would be considered a fluid. If you are trying to walk through a swimming pool, that would be considered walking through a fluid. Now, if you have air resistance, think about this. Just like when you stick your hand out the window, if the car is moving faster, there is more air resistance, right? So in the beginning, the ball is moving faster, so therefore it encounters more air resistance, so it's going to slow down more compared to when it is at the top. And in fact, so here we have our no air resistance trajectory in the red, and if you do have air resistance, you start to get this kind of curve with the dashed red line. And there's a couple of important pieces to note about this curve in particular. Now, the original curve without air resistance has a higher peak, right? Higher peak and a later peak. Not to mention, if you look at the original graph without air resistance, it is symmetrical. But the graph with air resistance is not. It takes a lot more time to get up than it does to come back down. So very important. All right, so we have our kinematics equations. You would have seen that last time. I hope you have your formula sheet handy. We're going to be using a lot of those formulas throughout this lesson. Now, using those kinematics formulas, we're now going to use them specifically in the x and y dimensions. So we're going to have to specifically start using subscripts, x for the horizontal and y for the vertical. All right, so here we go. Let's try this. Practice. A cannon fires a projectile with a muzzle velocity of 56 meters per second at an angle of inclination of 15 degrees. What are u sub x and u sub y? So first we got to figure out what the question's asking. And the question's just asking for the initial velocity in the x and the y directions. So again, I hope you have the slides in front of you right now so you have the question, because we're going to switch screens right now. We're going to solve this by hand. All right, so here we go. All right, so we have a cannon and it's firing, let's just draw something here. So we have a cannon and it's firing a projectile with a muzzle velocity. So here we go. So this thing is getting launched into the air. Now that velocity, so that's the initial velocity, so we're going to call that u. It's 56 meters per second. All right, angle of inclination of 15 degrees. What that means is it's the angle relative to the horizontal. Now, I can draw the horizontal wherever I want, but I'm going to draw it relative to where the ball is, since that makes sense. So relative to the horizontal, this angle here is 15 degrees. What are u sub x and u sub y? Okay, so what do we do here? So I'm going to take this and I'm going to draw it a little bit bigger. So here's that initial velocity vector. So u equals 56 meters per second. And we've got that piece here, so that's 15 degrees. So u sub x, that's the x component. So what I'm going to do is I'm going to define my x and y directions. So x to the right and y up define my positive directions. You have to include this. So in the last video, I mentioned that you don't necessarily always include this when you're working in one dimension, or at least you don't have to label whether it's x or y. But if you are working in two dimensions, which most of the time you are, you have to label the x and y, in addition to having the plus sign defined. So x is horizontal, so down here, if I take this vector and I resolve it into its x and y components, so in other words, this is the hypotenuse of a right angle triangle, and I have to draw the other two legs of the triangle. So the x leg will look something like this, and the y leg will look something like this. Okay, and I know that x and y meet at 90 degrees. So this down here would be u sub x, and this up here would be u sub y. Now, if you're wondering how I know that u sub x goes to the right and u sub y is going up, well, there's a couple ways to think about it. Well, first, if you can just imagine that projectile moving, it's moving up and it's coming down. So initially, it's moving up and to the right. So the x component's right and the y component's going up. Another way to look at it is when you add the x and y components together, you should get the original vector. Okay, so u is equal to u sub x plus u sub y. Right? When you add vectors, you add them tip to tail. So here's u sub x, and the tail of uy is attached to the tip of ux. And so how do you find the sum of these two vectors? By definition, you go from the tail of the first vector to the tip of the final vector. So this is the sum. What you just have to remember is, even though it's written like this is not linear addition. This is vector addition. So let me write that down. So this is not linear addition. This is vector addition. Okay, so what does that mean? It means you don't just add the numbers. So if you have u sub x and u sub y, you don't just add them. So if it's 2 and 4, you don't do 2 plus 4 is equal to 6. That is incorrect. Since they're vectors, you have to look at the picture. You add these two, because it's a right angle triangle, using Pythagorean theorem. And so in reality, this addition statement turns into u squared is equal to u sub x squared plus u sub y squared. And I know that can look confusing. How is this and this the same thing? You just have to remember that this is vector addition, and this is dealing with the magnitudes. This is the true way in which we calculate u. Okay, now we have a right angle triangle. We're trying to find the components. At this point, we're down to grade 10 math, okay? So something that I encouraged you to do last time was to make sure you can do this quickly. If I'm looking for the side of the triangle adjacent to the angle, then I take the hypotenuse and I multiply by cosine of the angle. So 56 times cosine of 15 degrees. Okay, so likewise, if I'm looking for the opposite side of the angle, which is u sub y, I take the hypotenuse and I multiply by sine of the angle, which is 15 degrees. Okay, so grab your calculators. So 56 times cosine of 15, so 54.1, and 56 times sine 15, 14.5. Okay, now those are still speeds. They're just in different directions. So 54.1 meters per second and 14.5 meters per second, respectively, in the x and y directions. Okay, so that's our solution for this first part, part A. Okay, when will the ball reach its maximum height? All right, so let's go back. So this was part A. This is part B. When will the ball reach its maximum height? All right, so I'm going to draw a quick picture again. So I've got this projectile that is launched, and in the absence of air resistance, it's going to follow a parabolic path, and it's going to hit again. Okay. Now I know the initial velocity is 56 meters per second. And I know the angle of inclination is 15 degrees. I want to know what the maximum height is. The maximum height occurs right here, right? Okay, so I'm trying to figure out what this is. Now, height is a vertical quantity. So what I'm looking for is s sub y, not s sub x, because that would be the x distance traveled, but s sub y. All right. Now, in order to find a y quantity, I need to use y information. So give me one moment. I'm going to just grab my formula booklet. So this is what one of the earlier slides was communicating. In the last video, we used all of these formulas in the 2.1 box, and we're still going to use them. The only difference is now you have to use subscripts. So you either are using these in the x direction or the y direction. You can use it in both, but you have to keep them separate. So in a single equation, if I'm using, for example, the second equation here, s is equal to ut plus 1/2 at squared, all of the subscripts have to be for x, or all of the subscripts have to be for y. You cannot mix x and y quantities in the same formula. Now, there is one quantity that is common to both the x and y dimensions, and that is time. So time, you don't have to put a subscript. And in fact, if you find the time in one dimension, you can plug it into an equation for the other dimension. Now, if that confused you a bit, don't worry, we're going to be solving all of these problems using the algorithm in which I just described. Okay, so again, we're working in the y direction here. So I always like to just indicate that. It's a good way of organizing yourself. So in the y direction, I know I'm looking for s sub y. Now I write down what information I know. It's kind of still like the grasp method. Well, I just found the initial velocity in the y direction. So u sub y is 14.5 meters per second. Right? I wouldn't use the initial velocity of 56. I have to use y components. Now, what else do I know? Well, when an object is moving under the influence of gravity only and it's a projectile, I know the acceleration in the y direction. It's going to be negative 9.81 meters per second squared. All right, now, how do I know that it's negative? Because in the beginning of the question, I defined positive y to be going up. And so acceleration is going down. It has to be negative. All right. Now I need one more piece of information in order to solve this. And that is going to come from you understanding the logistics of this problem. So there is something very unique about this maximum point. If you remember an earlier slide that had the blue balls representing the y motion and the red balls representing the x motion, we saw that the distance between, or not balls, the circles, the red circles were all equally distanced. And so that implied that the horizontal velocity was constant and there was no x acceleration. But in the vertical direction, the balls were getting closer together, or the circles, right? So at the very top, what's happening? They got so close, at the very, very top, the y velocity takes on a unique value. And at the very top, the y velocity is 0. Okay, that's very important. For projectile motion, the y velocity at the top is 0, not the x, just the y. So since I'm dealing with that point in particular, I can say Vy equals to 0. Okay, so I have SUAV. I need a formula that has SUAV. And if I look at my formula, here we go, the third one, SUAV, right there. Okay, so that formula is v squared is equal to u squared plus 2as. Now, since we're dealing in the y direction, I have to put the subscripts in my formula. So v sub y squared equals u sub y squared plus 2a sub y s sub y. I hope at this point you have practiced rearranging formulas enough that this next step will be comfortable for you. If you haven't, I strongly encourage you to go through the booklet posted on Teams again and practice your rearranging formula ability. If you're still having trouble, please let me know so that we can work on this. But in order to isolate for s sub y, it's going to become v sub y squared minus u sub y squared divided by 2a sub y. All right, so that's in one step. This is what you need to aim towards being able to do. Now v sub y is 0, and 0 squared is 0. So that is gone. All right, so that means I'm left with s sub y is equal to negative u sub y squared over 2a sub y. Okay, so negative 14.5, and that's getting squared, divided by 2 times negative 9.81. So grab your calculator. Now I can already see that this negative and this negative are going to cancel. So I'm going to just do that now to save myself the trouble of entering negative signs in the calculator. Divided by 2 times 9.81. So that's 10.7 meters, since this is a distance value. All right, so we found the maximum height. Oh, you know what? That's funny. My mistake, guys. I apologize. I was just looking for maximum height. I just realized that the question is actually asking for when the ball will reach its maximum height. But you know what? We actually didn't lose anything here because generally speaking, these kinds of questions do end up asking for the maximum height too. All right, so that's okay. So extra practice, so that's free, no charge. We are going to now solve for time. So my mistake, guys, I apologize. Let's look for the time. So imagine we didn't have SY. You could find the time using SY too, but we're just going to find it using what we were initially given, these pieces of information. Okay, so we have TUAV. All right, TUAV, that's going to be the first equation right there. V equals U plus AT. So V equals U plus AT. Now what I need to do is put my subscripts. So V sub Y equals U sub Y plus A sub Y T. Remember, T is time. Time is common to both dimensions. You do not put a subscript for T. All right, so V sub Y is 0, so that's gone. And we're solving for T, so T is equal to, so if I bring the UI over to this side, and then I divide by AY, it's going to look something like this. All right. Again, please become comfortable with rearranging formulas. If not, reach out to me as soon as possible. All right, so minus U sub Y, so that's minus 14.5 divided by minus 9.81. Well, that's a much simpler calculation. 14.5 divided by 9.81, so that's let's call that 1.5. Okay, 1.5 seconds. So it takes 1.5 seconds to reach the maximum height. Okay, so that is the answer to this question. All right. Now, I just want to point something out. On the slides, they have a slightly different way of solving the problem. If it confuses you what is being done on the slides, honestly, I would just stick with what I've done on the sheet of paper because this is how I'm going to show you the solutions for the homework problems as well. And this is really what I would expect in terms of a full solution for full marks on something like an evaluation. Okay. All right, C, how far from the muzzle will the ball be when it reaches the height of the muzzle at the end of its trajectory? Okay, how far from the muzzle will the ball be when it reaches the height of the muzzle at the end of its trajectory? All right, let's go back. So let me just go back to this picture for a second. So for part C, we're looking for when the ball reaches the height of the muzzle again. So, I mean, the muzzle would be right here, right? So if you look originally, the muzzle's there, there's the projectile. So it's literally right below it. So you can imagine that the muzzle's here lined up with that horizontal line. So we want to know what's this distance when the ball ends up back in this location right here. Okay, so we have to find now S sub X. So this is going to be for part C. Okay, so then the question becomes, how are you going to do that? Well, guess what? Actually, you know what? This is going to help us quite a bit. In part B, we found how long it takes to reach the halfway point, right? So from initial point to maximum point, it takes 1.5 seconds for the ball to go from here to here. And since we are ignoring air resistance, we know that the projectile motion takes the path of a parabola, which is symmetric. So if it takes 1.5 seconds to go from start to middle, it's going to take another 1.5 seconds to go from middle to finish. So the entire path, in other words, the time it takes for the horizontal distance to be covered is 3 seconds. So that's our first clue. So for part C, I know the time is going to be 2 times 1.5 seconds, which is 3 seconds. Okay, so we have that. We are looking for S sub X, how far it's going to be when it reaches the bottom. So S sub X is what we're looking for. Now, notice that we're dealing with the X direction here, not the Y direction anymore. Okay, so let me just write that on the side here. X direction. Now, what's so nice about the X direction is it's so simple. Because acceleration in the X direction is 0 and speed is constant, that means there is only one speed. And so you can call it V, you can call it U, it's up to you. We actually found the initial X velocity in part A. So U sub X is 54.1 meters per second, right? Now, if there's no acceleration in the Y direction, that value will always be 54.1 meters per second. So whether the ball is here, 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 or any other point you can find, the x component will always be 54.1 meters per second. That's very important. So this is what I mean. You can call this u or you can call it v because it's one and the same. So I'll just say u sub x equals v sub x, which is 54.1 meters per second. Now, this is something else. In your data booklets, they have every equation except this one. And that is that speed is equal to distance over time. So speed is equal to s over t. And you can only use this when acceleration is 0. All right. So in a way, the formula is, in a way, in the formula sheet. So if you look at the second one here, s equals ut plus 1/2 at squared. If acceleration is 0, you have s is equal to ut. Distance is equal to speed times time. Or if you rearrange it, speed equals distance over time. But again, it's only when acceleration is 0. And so v sub x equals s sub x divided by t. And since we're looking for s sub x, I'm going to rearrange that. So it's v sub x times t. All right, so that's 54.1 times 3. So grab your calculator. 54.1 times 3. That's 162.3 meters. All right, 162.3 meters. That is how far the ball will be from the muzzle when it reaches the height of the muzzle again at the end of its trajectory. Okay, so let's go back and move on. Oh, by the way, let me just go back for a second. If some of you are looking at these answers and you're wondering why it's a little bit off from what we're doing on the sheet, the reason is the answers on the slides account for significant figures, and that's specifically for IB. Since, I mean, if it's not an IB class, they don't need to worry about the sig figs. IB students do need to pay attention to the sig figs, but you can go by the answer that I'm using here on the sheet. So the 162.3. All right. D, sketch the following graphs. A versus t, v sub x versus t, and v sub y versus t. Now, sketch, right? So we don't have to go and make a big production of this. Let's do this. Okay, so grab your ruler. We're going to do A versus T first. Now, let me do it like this. So remember, whenever you have something versus something, the first piece there, that's always the y, or the dependent variable, and the second one is always the x, or the independent variable. Now, I'm only going to be drawing quadrants 1 and 4. And the reason for that is because time always has to be positive, right? You can't have negative time. It's a sketch, so I really have to just put something simple here. Now, what I do know is that acceleration throughout this entire projectile's motion, the only acceleration present is acceleration in the y direction. There is no acceleration in the x direction. So any acceleration that there is ay, since, and if any of you have never seen that symbol before, the upside down therefore symbol is since, so the three dots in an upside down triangle. So let me just write that in. Since a sub x equals 0. All right, but what is acceleration in the y direction? It's about negative 9.81. So it's a negative number, so maybe we can say it's about here. So let's do this. So negative 9.81 meters per second squared. All right, so that's a graph of acceleration versus time. The next thing we have to draw is v sub x versus time. All right, now v sub x, the x velocity. We were just talking about that in the previous part C. I said that since there's no acceleration in the x direction, the x velocity initial and final and any point in between is constant. It's 54.1 meters per second. So similar to how we did this graph for acceleration versus time, we're going to do the graph for v sub x versus time. Again, time is only positive, so I only draw quadrants 1 and 4. Okay, so this is, oh, I didn't label my A here, so let me label that. So that's acceleration, and this is V sub x. Now I know V sub x, so 54.1, and that is a constant value throughout. 54.1 meters per second. Okay. And the last graph we have to draw is V sub y versus t. V sub y versus t. Again, time is only positive, so only draw quadrants 1 and 4. By the way, if you're wondering why I keep referring to quadrants 1 and 4 in mathematics, so this is quadrant 1, 2, 3, and 4. When you get to grade 12 calculus, you'll get to learn about octants, and so the third dimension. But for now, just the 4. Okay, so V sub y. Well, let's think about this. When you look at the projectile, when it starts off with a y velocity of 14.5 meters per second. We know that at the top it's 0, and when it comes back down, it's going to be 14.5 again, but not positive 14.5. It's going to be negative 14.5. Now, something to remind ourselves is that, let me write it here, recall that the slope of a VT graph, whether it's V sub x, V sub y, or just V, the slope of a VT graph is acceleration. And so therefore, it would make sense that if this is the V sub y t graph, then the slope should be acceleration in the y. Acceleration in the y is negative 9.8, or we can just approximate that to be negative 10 for simplicity. So that means the slope of this graph has to be negative 10. And I know that I start off with a y value of 14.5. And I know that after however much time has passed, which I think we determined it to be 3 seconds, after 3 seconds, it's hitting negative 14.5 meters per second, right? And at 1.5 seconds, it's at the maximum point. So therefore, it's going to cross here. So we have 1 point here, 1 point here, and 1 point down here. Okay, and so that is our graph for V sub y versus t. All right, let's go back to the slides. All right, there's going to be a lot of these types of multiple choice questions throughout the way, so let's do our best. Which one of the following is a true statement concerning the vertical component of the velocity and the acceleration of a projectile when it is at its maximum height? All right, so we have two options for acceleration. Either it's 0 or g, and the vertical component of the velocity, either it's the maximum or it's 0. All right, this is where students who are initially introduced to projectile motion sometimes make a mistake. When you look at the projectile motion, you can see that the vertical component of the velocity at the maximum point is 0. We already determined that in the previous problem. So that means that A and B are incorrect. But what about the acceleration? For many students, it is very tempting to say that the acceleration at the top is 0. But what they fail to understand is that if the acceleration at the top was 0, then that speed wouldn't change, right? In order for that speed to start increasing as this object starts falling back down, there has to be an acceleration. Again, by definition, acceleration is velocity changing with respect to time. So throughout a projectile's motion, there is always gravity acting on it, no matter where that object is, whether it's sitting on the ground, whether it's in the air, there's gravity always acting on it. So while it's in the air, it does feel the effects of that acceleration, and that acceleration is g, the acceleration of free fall. Therefore, the answer is D. Okay. All right, so there we go. A stone is thrown at an angle to the horizontal. Ignoring air resistance, the horizontal component of the initial velocity of the stone determines the value of what? The range only, the maximum height only, the range and the maximum height, and the range and the time of flight. All right, so I'm going to start from the bottom. So range this is actually a new piece of terminology which I haven't introduced yet, so let me introduce that now. Excuse me. Range, and actually, you know what? Let me actually show you this on this sheet of paper in this problem. In this problem, in part C, we had to find the x distance that the projectile traveled through. This s sub x, this is called the range. Okay, and I know that can get confusing because in mathematics, whenever you hear the word range, you think of y, since the domain is associated with x. But in physics, when someone asks you for the range of a projectile, it means how far horizontally did it travel? How far did it travel in the x direction? Okay, so make sure that's clear. So that's why they all, well, most of them have range. We're talking about which one of these is influenced by the horizontal component of the initial velocity. So the horizontal component of the initial velocity is going to affect horizontal quantities. Okay, so it's not going to affect maximum height because that's a vertical quantity. So B and C are out. Now the trouble is it just affecting range or range in time of flight? So something that I kept mentioning is that time of flight is for both dimensions. So it's affected by the x and it's affected by the y. So we cannot put this here because both components determine the time of flight. Therefore, the only possible answer here is part A. Okay. Next, a stone is thrown horizontally from the top of a vertical cliff of height 33 meters as shown below. The initial horizontal velocity of the stone is 18 meters per second, and air resistance may be assumed to be negligible. State the values for the horizontal and for the vertical acceleration of the stone. Now, I know that this part of the question is very simple, but what I would like you to do is sketch the diagram from this problem onto your sheets. Okay, so we have a cliff, and we have water, and we have a stone that is being projected horizontally. Now that's important. There's going to be some questions where the stone is on a cliff and it gets thrown up, some questions where it gets thrown down, and some questions where it's projected horizontally. Okay, so you got to make sure you're able to handle all of those scenarios. So we have 33 meters as the height of the cliff. This is sea level, and this thing is being projected at 18 meters per second. And I'm just going to call that U here since it is U. Excuse me. By the way, I apologize for all the sniffling. My allergies are acting up again, unfortunately. All right, so back to the problem. State the values for the horizontal and the vertical acceleration. Well, horizontal, it's projectile motion. And projectile motion, by definition, is motion in which the object is only influenced by the force of gravity. And so if only the force of gravity is acting on it, that means only acceleration due to gravity is acting on it. So if that's the case, that means there's no horizontal acceleration. So a sub x is equal to 0. Vertical acceleration is always going to be that due to gravity. So negative 9.81 meters per second squared. Something that I do want to start writing here, I have to define my positive x and y directions because that is a two-dimensional problem. So I'm going to define that. I'm going to just let positive x be right, positive y be up. Okay. So there we go. It's negative 10 here because sometimes in the slides it's just rounded, but I would like you to use negative 9.81 as it is in the formula booklet. Okay. B, determine the time taken for the stone to reach sea level. Excuse me. So let's think about the trajectory this stone's going to take. So this stone gets projected horizontally and then it starts falling under the influence of gravity and eventually it falls into the water, right? We have to find the time taken for it to move through this entire path. Well, let's think about this. If we work in the x direction, well, actually let's write down what information we know and we'll organize it according to x direction and y direction. This will help us see what process and what path we should take. And this was part A, this is part B. Okay, now since the stone is initially projected horizontally, I know that that U is in fact U sub x, right? Because it's purely horizontal motion. So I know that u sub x is 18 meters per second. And the fact that it is projected horizontally initially means that there is no initial component of velocity in the y direction. That's really important. I know that from where the stone begins to where it finishes, there is a vertical displacement of 33 meters down. And this is going to be negative because I define positive y to be up. So S sub y is negative 33 meters. Something else that I automatically know in the y direction is the acceleration, and that is negative 9.81 meters per second squared. So I already have 3 pieces of information in the y. In the x, that's really all I have. So because I'm looking for time, I have to use the y direction. Remember that time is the piece that unites x and y, right? It's the only quantity that's common to both directions. All right. So I need something with S, U, A, and T. So looking at my formula booklet, S, U, A, T, well, that appears in the second formula, okay? S equals UT plus 1/2 AT squared. Since we're dealing with the y direction, I have to put the subscripts. S sub y equals U sub y, T sub y plus 1/2 A sub y, T squared. Oh. My apologies, no t sub y. That is a dimensionless quantity. Okay, u sub y is 0, and that's always nice because now the 0 times t is 0, so that disappears. Excuse me. And so that means we're left with a sub y equals 1/2 a sub y times t squared. Now we are looking for t squared, so we're going to rearrange this formula. So t is going to be equal to 2s sub y divided by a sub y square root. If you didn't see how I did that, please pause the video right now and do it step by step until you get comfortable doing it in one step. If you need to do it in more steps, take your time, and that's completely fine too. Okay, so at this point we're going to plug in our values. It's a little weird, I'm going towards the left here just in the interest of space on the page. So t is equal to, and oh, something else I should point out. I think I pointed this out on an earlier video. Whenever you take the square root of something, you're supposed to end up with a plus and minus roots, but you can't have negative times, so we just ignore the negative root. Something just to keep in mind. Whenever you do problems in math class, don't just assume the negative root disappeared. So 2s sub y, so 2 times negative 33, divided by negative 9.81. The negatives cancel. So 2 times 33 divided by 9.81, square root 2.6. All right, so it takes 2.6 seconds for the stone to reach sea level. Let's go back to the slides. Part C, calculate the distance of the stone from the base of the cliff when it reaches sea level. So how far is the stone? So let me go back to the page. So what we're looking for is the distance from here to here, right? So this distance is called S sub x, and we just said that there's a name for that. It's called the range. And so we're looking for the range of this projectile. That is in the x direction. So S sub x is equal to question mark. Since we have u sub x, we're looking for S sub x. In the x direction, remember that the acceleration is 0. And so the only formula that we really need to use in the x direction, looking at this now, I probably should have solved this down here. Okay, that's fine. So let's continue part C down like this. So let me just rewrite this quickly. In the x direction, we have u sub x, 18 meters per second. There's no acceleration, so I know the velocity is constant. S sub x is what we're looking for. So the only other piece of information we would need is time, and we just found that in part B. Since time is common to both of them, I know that the time it takes for this projectile to go from the top of the cliff to hit the water is 2.6 seconds. So that's the same distance it takes to travel this horizontal distance or this vertical distance. Okay? So 2.6 seconds. And remember I said that for the x direction, as long as a sub x is equal to 0, we can use the formula speed is equal to distance over time. And so we're looking for s, so that's going to be equal to speed times time. And we're going to make this for the x direction. So putting in my subscripts. So S sub x is equal to V sub x. So this is effectively V sub x. That's 18 meters per second times 2.6 seconds. 18 times 2.6, 46.8 meters. Okay, or if you want, you can call that 47 meters. That's fine. All right, so it lands 47 meters from the base of the cliff. All right, part D, calculate the angle that the velocity makes with the surface of the sea. All right, this is a very common ending question for a projectile motion problem, not just for this one. These kind of questions even show up in grade 12 physics when we're studying about electric charges being accelerated through a magnetic or electric field and the angle that they make when they're hitting some type of surface. Okay, so this is not a unique question whatsoever, but it is an important one. All right, so let's go back to our page. I want to go to the picture for a moment. The angle that it makes when it hits the surface of the sea. So that happens right here, right? It hits at some angle. It's not necessarily hitting vertically, but it's hitting at some angle. So if you look at this part right here, so let me just show you what that looks like. How am I going to do this? Okay, there we go. So I've got this arrow that's coming down. This is its incoming velocity, which we can call V, right? All right. Now that velocity can be broken down, or it can be resolved into x and y components. So the y component is going down and the x component is going to the right. So this is V sub x and this is V sub y, and of course they meet at 90 degrees. Now let me take this picture now and copy it onto my new sheet of paper here. So I have my velocity. This is part D. So this is V, and V is what I'm trying to find so that I can figure out the angle that it makes with the surface of the water. V sub x, V sub y, and I mean this is effectively the surface of the water, right? Okay. So if I want to find the angle that it makes with the surface of the water, essentially what I'm doing is I'm looking for this angle right here, right? Theta. Now, in order to find theta, I need V sub y and V sub x. I actually don't even need V. Okay? I need V sub y and V sub x. And I already know one of those right away. In part C, and actually in the previous parts, I've already established that in the x direction, since acceleration is 0, the x velocity is constant. Okay, so u sub x is equal to v sub x. At any point in time, the x velocity is 18 meters per second. So v sub x is equal to 18 meters per second. What I have to find is v sub y. Once I find v sub y, I have these two sides, and I can use tangent of theta, or rather the inverse tangent of theta, of vy over vx, and I'll find theta. So that's the simple part. All right, so now how do we find the final y velocity? Well, let's look at our picture again. Looking at the original circumstance, I know that the initial y velocity when this thing starts is 0. And I know that by the time it gets down here, let me not go down too much, by the time it gets down here, not only has this taken 2.6 seconds, right, but it's traveled 33 meters through this kind of displacement, right, negative 33 meters or 33 meters down. I know that the acceleration is this value. So what I could really do is use u sub y, s sub y, a sub y, right, with all three of these pieces of information, and then look for the v sub y. What is the final velocity after this ball has displaced itself down 33 meters? Okay, so that's what I'm going to do here. So using u sub y is equal to 0, so this is y. Using u sub y equals to 0, s sub y equals to negative 33 meters, a sub y equals negative 9.81 meters per second squared. I'm going to find v sub y. So I need a formula that has s, u, a, and v. S, u, a, v, that's the third one. Okay. At a certain point, you're not even going to need to look at the formula sheet anymore. You're just going to inherently memorize them without meaning to. All right, so we've got v squared equals u squared plus 2as. And we're dealing with the y direction, so I have to put the subscripts in. U sub y is 0. 0 squared is 0. So that's gone. V sub y is then the square root of 2a sub y s sub y. So square root of 2 times negative 9.81 times negative 33. The negatives cancel. So 2 times 9.81 times 33, square root, and we get 25.4 meters per second. Okay, so that's V sub y. So we have V sub y, we have V sub x. Now we can use those two in our triangle to find the angle. So that's 90 degrees. This is 18. This is 25.4, and we're looking for theta. Okay, since we have the opposite and adjacent side, we're going to use the ratio tangent of theta. Tangent of theta is opposite over opposite over adjacent. So 25.4 divided by 18 is 1.411. So theta is equal to the inverse tangent of 1.411, and that repeats. So inverse tangent, 54.7 degrees. Okay, and that is our final answer. Therefore, the angle that the ball makes or the stone makes with the surface of the water is 54.7 degrees. Let's go back. All right, let's try this next multiple choice question. A stone is projected horizontally from the top of a cliff. So this is just like the previous one. It's projected horizontally. So you already know that the initial vertical component of the velocity is 0. Neglecting air resistance, which one of the following correctly describes what happens to the horizontal component of velocity and to the vertical component of the velocity? All right, well, I'm going to go back to the picture here because this diagram is just going to be really helpful for us. So we're trying to see, and it's the same situation pretty much. You're projecting the stone horizontally, and you want to know, well, what's happening to the horizontal component of velocity and the vertical? Well, let's start off with the easy one. Horizontal component is going to stay constant, and that's not because it was projected horizontally. It's because in projectile motion, ignoring air resistance, there's no acceleration in the x direction. So that means if it starts at 18, it's going to be 18 throughout the entire motion. So that's constant, which means we can already remove options A and B. All right, now you have to figure out if the vertical component is constant or if it increases. And in the case where you initially project yourself horizontally, this thing is just falling down, and so it's gaining speed more and more and more. Okay, so the vertical component of the velocity must be increasing. Hence, the answer is D. All right, let's give this problem a try. A ball is projected from ground level with a speed of 28 meters per second at an angle of 30 degrees to the horizontal as shown. There is a wall of height h at a distance of 16 meters from the point of projection of the ball. Air resistance is negligible. Calculate the initial magnitudes of I, the horizontal velocity of the ball, and II, the vertical velocity of the ball. So just like the previous problem, the first thing that I want you to do is redraw that picture into your notebooks. And that's what I'm going to do as well. Okay, so here we go. So this is another example. And we're dealing with part A, I, and II here. All right, so the picture looks something like this. So we have the projected ball. This is the floor or the ground. And this thing is taking a parabolic path, of course, because it's a projectile. And at some point, it's going to just clear a wall. All right, and this wall has height h. This is 30 degrees. The wall is 16 meters from the initial point of launch. Okay. And the initial speed is 28 meters per second. So even though that's not in the picture, it's given in the information in the problem. All right, so good. All right, so we have to find the initial horizontal velocity of the ball and the initial vertical velocity of the ball. Let me grab a different color. Give me one moment. Okay. So this is the initial velocity. So what I can do is I can break it down into a horizontal component like this, and I can break it down into a vertical component like this. So this would be u sub y, and down here this would be u sub x. And we already know how to find these values. So for part I, u sub x, it's adjacent to the angle, so it's going to equal the hypotenuse times cosine of 30 degrees. 28 times cosine of 30, and that's 24.2, and that's meters per second. All right, and u sub y is equal to the hypotenuse times sine of the angle. So 28 times sine of 30 degrees, that's 14. Okay, in case you didn't notice, sine of 30 is 1/2. Okay, so 14 meters per second. All right, so those are the answers to I and II. Okay, let's go back to the slides. All right, B, the ball just passes over the wall. Determine the maximum height of the wall. All right, this one, well, this is going to be a little interesting. We got to find the height at this point, right? So yes, we're looking for the height of the wall, but we're also technically looking for the vertical displacement of the projectile at that point. So another way of looking at it is I am looking for S sub y at that particular point, right? So at that particular point, I know that the S sub x value is 16 meters. Now, I know what the initial x velocity is. I know that the distance to get to the wall, the horizontal distance or the range, is 16 meters. So using those two pieces of information, I can find time. Because remember, in the x direction, I have no acceleration. So there's only 3 quantities that I deal with: speed, time, and distance. All right, so I can find time from the x direction and then use time to help me find sy in the y direction. Okay, I hope that makes sense. So for part B, I know that in my x direction, I have S sub x is 16 meters. I have U sub x is equal to 24.2 meters per second. And since A sub x is equal to 0, well, I can use a very simple formula. So I'm just going to find t. Speed is equal to distance over time. Right, so that means rearranging for time, it's going to be distance over speed. Okay, so S sub x is 16 meters. Divide that by 24.2 meters per second. 16 divided by 24.2, 0.661 seconds. Okay, so pretty much what we just found is that it takes 0.661 seconds for the ball to reach this point, right? To travel this horizontal distance, which is equivalent to it traveling, oh, sorry for the in and out of focus there, for it to travel this horizontal distance and therefore for it to get to that point. So that's the same time for it to travel this vertical distance as well. So now we're going to go to the y direction. And since time is the quantity that's the same in both dimensions, I can automatically say that I know that t is 0.661 seconds at that point. Now what I'm looking for is S sub y. Another piece of information that I know that I calculated in part A sub II is U sub y, 14 meters per second. And yet another piece of information that I know that is not always given in the problem, in fact it usually isn't when it's a projectile motion problem, is acceleration in the y. It's negative 9.81 meters per second squared. So I need to do something that I should have done at the beginning of the problem, and that is define where my positive and negative x directions are. Positive y up, positive x to the right. We gotta always define this. All right, so I have T, U, A, and I need to find S. Looking at my formula sheet, S, U, A, T, I'm looking at the second formula right there. Okay, so S is equal to UT plus 1/2 AT squared, and put the subscript Y for all your quantities except for time. All right, so here we go. So 14 times 0.661 plus 1/2 times negative 9.81 times 0.661 squared. All right, so 14 times 0.661 plus 0.5 times negative 9.81 times 0.661 squared. 7.1 meters. It's a pretty reasonable value, 7.1 meters. So therefore, the height of the wall, the maximum height of the wall is 7.1 meters. Let's go back. Okay, next problem. A ball is kicked at an angle to the horizontal. The diagram shows the position of the ball every 0.50 seconds. The acceleration of free fall is 10 meters per second squared. Air resistance may be neglected. All right. Using the diagram, determine for the ball the horizontal component of the initial velocity. So what a lot of students want to do with this is find the slope between the first and second point, because they remember that the slope of a displacement time graph is velocity. But this is not a displacement time graph. It's a vertical displacement versus horizontal displacement graph. So this is actually what the ball would look like moving through the air. So in order to find the horizontal component of the initial velocity, I need to know how much horizontal distance it traveled and how long that took. Well, I do have information about time in this question. I know that each dot in this graph was taken every 0.5 seconds. So the distance between the first dot and the second dot, which would represent the initial components of the journey of this ball, okay? I know the time between these two dots is 0.5 seconds. The time between the next two dots is 0.5 seconds, but really I just care about the first two dots right now. So this time is 0.5 seconds, and based on the horizontal scale, I can figure out the horizontal displacement. So from this dot to this dot, that's 4 meters, okay? So in 0.5 seconds, it covered a horizontal distance of 4 meters. Well, you know how to calculate velocity, especially in the horizontal direction. Right? So V is what we're looking for, V sub x. I know the time is 0.50 seconds. And the horizontal displacement S sub x is 4 meters. So S sub x over t, so you're going to get your speed. So that's going to be 4 meters divided by 0.5 seconds. Half of, well, if you divide 4 by half, you get 8. So that's 8 meters per second. That's your horizontal velocity initially. Oh, and I realized I labeled that C. That should have been labeled part A, I. This is a new example. Okay. All right, so back to this. All right, I, again, using the graph, determined the vertical component of the initial velocity. Well, I know that the ball undergoes a displacement of 11 meters based on the graph vertically. And so if that also takes 0.5 seconds, then I know the initial velocity of the ball can be approximated by 22 meters per second. This is not the best approximation, but it is an appropriate approximation because after all, the data points on this graph are taking into account the acceleration due to gravity. Okay, so if you have 11 meters and you divide that by a half, that's essentially doubling 11 and you get 22 meters per second. All right, part 3, the magnitude of the displacement after 3 seconds. All right, so remember that displacement means how far are you from where you started? All right, and remember, this is actually the trajectory of the ball as you would see it in the air, since it's displacement versus displacement. Okay, so since each gap represents half a second, so the first gap is half, and then we're at 1 second, then we're at 1.5, 2, 2.5, 3. So the point immediately after the peak is the 3-second mark. So what we want to know is the distance between where we start and that point right there. And that's the distance right there. And so what we do is we break this up into a right angle triangle, since in order to find this distance, we can just find the legs of the right angle triangle and use Pythagorean theorem to figure out the length of the hypotenuse. So the base of this triangle, I can clearly read it off the graph. It's 24 meters and the height is 30 meters. So that's all I need to do here. Use Pythagorean theorem, d squared equals 24 squared plus 30 squared, and solving that will leave you with d is equal to 38 meters. Now, on this slide, they also solve for the angle, which you could do, what's the angle based on where it started? Or if the question had asked, what is the displacement after 3 seconds? Then yes, you would have to find the angle too. So simply doing an inverse tangent of 30 over 24 to give us 51 degrees relative to where we started. 51 degrees above the horizontal, that is. The reason why you don't necessarily have to find that in this question is because the question says find the magnitude of the displacement, right? So if it just said find the displacement, you would say 38 meters at 51 degrees above the horizontal. Okay. On the diagram above, draw a line to indicate a possible path for the ball if air resistance were not negligible. So it's been a couple of slides since we looked at this, but there was two main points you have to remember. The first is that when the ball is under the influence of air resistance, it's not going to be able to travel as far in the horizontal direction, nor as high in the vertical direction. So the peak is shifted down and to the left of where it was when we ignored air resistance. So that would be an appropriate location for the peak. It doesn't have to be exactly there, but it might be a little bit to the right or left, but it has to be to the left of the original peak and lower. All right, the other piece is that in order to get to the original peak, it's going to take longer than it's going to take to come down. Remember, when you're going up, you're fighting against gravity, you're fighting against air resistance, and on the way back, gravity's helping you come down. So you're going to come down much faster. So just a couple things to keep in mind. It's no longer symmetric if you are dealing with air resistance. Okay, and that is the end of lesson 2.1 motion, part 2 of 2.